Let's go ahead and hit on Ada's question. Wow, would not the vibrations cause spalling, cumulative, not like an all at once explosive? Would not like an all at once explosive? That's sort of like fracturing of a glass. You see, guys, a glass burst. Would there not be cumulative evidence? Question. Cumulative evidence, like facade cracks starting from the bottom and increasing. Like facade cracks starting from the bottom and increasing. All right, so let's talk about frequency and resonant frequency. And what a lot of people confuse when a guy's jackhammering outside, or when they're doing a roller, for example, or tamper and things like that. People confuse the roller destroying their property when they hear their windows when their windows start rattling. They assume that the windows are rattling means the ground is shaking, and that their building's falling apart. Excuse me. What it is the resonant frequency is the frequency. Let me see if I can move over a couple of times. The resonant frequency of sand is different than the resonant frequency. So you can see that this dry sand bed has a resonant frequency of 233.7 hertz. So these tampers and things like that, when you're tamping soil and consolidating soil, it really would behoove you to have a machine that could change its frequency. We often use jack tampers, they're called, jumping jacks, etc. They jump up and down to try to not get, to compress the soil, to get them to consolidate together. And we do that because a plate tamper will get surface tension and get stuck. It won't move with the moisture coming up from clay. And so you use a jack tamp to try to get the same consolidation, meaning making it tighter. But reality, a good to know your frequency, it was better to be able to dial in your frequency of your roller. And rollers have a lot of higher, better rollers, especially from Germany, have an ability to adjust the frequency. And we just adjust it randomly without really taking in the data of what's actually going on with, say, asphalt as you're doing it. Each one is going to behave differently. A non-slump, because now we're doing roller concrete materials, using a roller just like you're doing asphalt. And a 9 slump is going to behave differently under that roller and vibration than a 7 slump, than a 5 slump, than a different material composition. They're going to behave differently. The testing should be done of cubes after you roll. Then you can, and if you kept the frequency the same and you knew your mix, your concrete design mix, you would then duplicate that if it gives you your required PSI. Coming out of that changes your frequency, and no longer your resonance frequency and of that material would become your resonant frequency to get you that PSI. Now, resonant frequency is done differently though to determine the failure of each item, each object. So an eyeball, for example, has resonant frequency, I think it's like 19 hertz or something crazy like that, where if I could get your eye to fluctuate at 19 hertz, I could have your vision go south on you. Your vision starts acting up. So resonant frequency of, let's see, eyeball. Let's see if this works. Oh, there. Look, I didn't search it. Yeah, 19 hertz. Yeah, so I don't like sharing some of this stuff that I know with you guys because some people can use it for bad. And so, yes, I know a lot of things that I don't want to share with you. For example, this is a form of torture, actually, that you guys don't know about. So it's a form of torture, and the person wouldn't even know what's going on if you don't let them know. But there's a resonant frequency of your heart, of everything has a resonant frequency where it will start acting up. We just can you get to it is the question. So the more dense a material it is, the faster sound travels, etc. So let's, etc. I guess I kind of blew that off with the etc. part. This is numerical evaluation of soil behavior during pipe piling installation using impact and vibratory driving in sand. Well, this is just this study and related to their equipment and where it was placed. that day, the humidity, moisture content, all of that matters. So yes, these are studies I'm reading and studying and researching. But it doesn't mean that all sand is going to behave that way. I would beg to differ that the sand at the edge of the beach where the water hits is totally going to be a different resonant frequency than sand further back, composed of a different density. So I have a video I'm working on for you guys. Now it's going to be ultrasound dealing with and water, like the clicks from a dolphin and also from a ship. How it basically ignores the water moving around left and right or north and south, whichever direction. It ignores it. It does travel faster and colder and at different speeds, rather, and hot and more heated surfaces. The more dense, however you get there, the more dense a product is, the faster it will travel. So the frequency, then that's a generalization, but the generalization is pretty solid. It's a pretty good generalization. So the frequency range is 10 hertz to 40 hertz on concrete, and this is resonant frequency of concrete. Okay, so now we go to non-destructive detection of rebar buried in reinforced concrete wall with wireless passive SAW sensors. All right, isn't this amazing? So as you can see, there is a way for NIST and even the people suing both directions based on that you can find the resonant frequency of that wall that's existing right now. Now you have to sonar test it first to see if you can find cracks. So sonar testing is another non-destructive, theoretically non-destructive because it's only this, sound. It does have a frequency, but it's not to the point where you're going to meet that frequency of causing the concrete to fail. It's not there. So let's see if I can do this. I've lost my brain on the sensors. And the wall. So the wall is here. I'm thinking of these damn sensors. I'm trying to think of the name of it. That's what I'm really lost in my brain. It's interesting when I jump ship from one thing to another. It takes me a moment to I see the sensors to get their name to them. It's the way I work. My brain operates. So if you can run the transducers, that's the sensors I'm referring to. If you could run the transducers up and down this wall, if you had access to it. So if the 87 Park, if you have your lawyer and your engineer say, oh shoot, that's a good choice, you would get access through subpoena power, whatever power it is, and you want to exercise it on this wall. You want to go out there with your transducers and have a person look for cracks in the existing wall there. And you're going to find that if you're lucky, you'll find no cracks. If you do find cracks, well, then it was caused by them demolitioning. If you find no cracks, that shows that it was even in spite of demolitioning, the wall is so stable. And you would look all the way down there at the floor. So here's I guess I go show orient us. This is the sheet piling that would be at Champlain Tower South, and I don't know where it ends, where it stops. All right, so we're just taking liberty with this there, and I should guess I'd shrink it down to the level with the concrete. And actually, it would be more like this because a little bit of concrete going down because the floor has been removed, and so you would see the steel here. So you can also check this steel, the sheet piling, for its characteristics. You can actually put creating, since you know the frequency, that if you can locate, and this is where you would attack your own, if you will, your own CV5 to say that, hey, where were those sensors exactly? And when they can't tell you where they were exactly, you'd say, well, the data, it matters where they were exactly where they are. Not well, they were roughly here, they were roughly there. This is an exact thing because in the sonar, the system they use has a ricochet problem, and it can increase your volume because remember, metal goes faster. And look at the top view of the sheet piling is something like this. All right, and then let's do a little angle in there. So if they're driving sheet piling, let's just call this CTS, right? I'll just put C there for now. And on this side we have 10 feet. Is it 10 feet from here? Great. 10 feet from there? Where did it determine 10 feet? Or is it 10 feet from here? With that said, you can imagine the sound if you were driving in sheet piling, say let's do another one right here. And you've got your sensor here, and this is 87. So this will be 87 right here, park. All right, it's 87. And you have your sensor here. Well, it's so close to here that it's going to pick up more, it's going to indicate higher than if it was here, the drop-off, right? Your drop-off. But if you get closer to here, it'll pick up, but it might also be getting a pickup from the back wall. And how much of it, even at here, how much of it is a ricochet off that wall to there? This is the angle of incidence of the sound, if you will. We don't know the angle of incidence of that because we don't have the so an echo is an angle of incidence, right? It comes back at you. You hear your own voice, angle of incidence. And here is so if I was standing here and I was able to direct my volume here, it would, if I can get this to come right back at me, my angle of incidence is I'm pretty much squared up with it. It's coming right back at me. But if I talk in this direction, it would ricochet off of here, hit this wall, it would come down, hit this wall, slide off. It might ricochet on an angle and get absorbed in here even more. As it's getting absorbing, the frequency is changing. The frequency is changing as it goes further away. Now, there's the ricochet problem. How you can make NV5 throughout all their data is you say, where was it exactly in relationship to the meter that they're claiming that these 5 was? They say the 0.5 action, half an inch, I think it is, right? Where was it exactly in relationship to the profile? Where was it exactly in relationship to your sensor? Where was this in relationship to the sensor? Where were they in relationship to each other? And that's when you start. And then where's the equipment? Where was the equipment that was giving a reading? Again, how long did they peak there? You just can't, peak one time and break my glass. Yes, the resonant frequency of this might be, let's say 70 hertz of this glass. It's, I'm sorry, I want you to visualize your screen. And say I can hit it. Well, maybe I only hit it for a second, a moment. I didn't stay at the resonant frequency. And then that resonant frequency, I stay there until a fracture develops and then failure, right? But once a fracture happens, let's say I'm able to crack find the resonant frequency of your cell phone. You drop it, it can't take the flexual, right? That's more of a tension break. But let's say I can find the resonant frequency of your laptop or whatever it may be. Let's put the screen here. This is the screen. And so we send a resonant frequency in, however it's making this thing sing. Now say it sings it like it responds at say 70 hertz. Let's just use that number there. 70 hertz. This one is going to respond at maybe 80 hertz. Now, a different size computer screen, this might be 90 hertz. Same glass, same material, but the shape of it would matter too. This resonant frequency is going to change on what's the failure. It's not all glasses break at the same frequency, right? It matters because the density ratio changes, and then you're going to get your resonant frequency changing per your screen. Of course, it changes what you're watching too. If you're watching no, I'm only teasing on that. I can't. I won't tease this time. I can't help it. I'm a practical joker. So that's why I do some of my videos that sort of for fun. And then some I want to see with some comments. So, I say for fun when I troll a bit. You guys call it trolling. Me, I just love psychology. So this changes. Your resonant frequency would change on a square screen versus this size screen. It all changes, right? And now we come back to the cumulative effect of what the Ada stated. So Ada, if you can imagine that this sand has a resonant frequency. It's now absorbed the sound vibration, the vibration from here, the frequency from here. It was interpreted as X frequency, right? Whatever the numbers are, and the hertz, right? So it's interpreted as these many hertz. Right here, what are the hertz back here? We don't know. What is the hertz of this steel to make it then vibrate? It might be nothing. In other words, you can scream to your blue in the face in your house, turn the TV up and play the music, and you can't get the windows to break. But sometimes you can turn up your music so loud or to get the right frequency that your own speaker breaks because you found the resonant frequency of that speaker. And then your speaker goes south. You broke it because you found the right one. I remember Dirty Diana cost me 2 speakers. Now, I can play Dirty Diana. Remember, what's his name? You know what I'm talking about, the song. I played on many other speakers, never causing them to fail because that frequency wasn't there. But I happened to hit that day. I happened to be playing Dirty Diana on these set of speakers, and I kept it at the right tone and elevation, the amount, the right amount of time when he went into Dirty Diana. And boom, those speakers were trashed. Now, I got the same speakers again under warranty. I played Dirty Diana again, but I never was able to find, because I tried to have a little fun to see if I could make it fail again. Couldn't help it. And I could never find that right volume again. And also, where they were located, how they were on the floor. You got them on the floor, it's going to react differently if I put the same speakers now on carpet, or I put the same speakers now on a bed, using the same frequency that it caused them to fail, say a moment ago, on a table. So it's not the same. All right, they're not the same. So the frequency changes now. Your failure frequency, this frequency does not correlate to the same frequency in the building. Now you asked about the structure. So it's got to go through all of that concrete, this little bit of frequency down here. It's got to go through the steel and then find the resonant frequency of that steel, causing it to vibrate and start sharing it through into the concrete. From there, it has to find the resonant frequency of the concrete and then cause a failure of the rebar connection. And let's find that non-destructive wall system. And so when you see people like that report, it's written by a lawyer and not by someone who can break it down and debunk it like myself, saying, all right, well, it's nice to be right, but it's better to have a cite, is what lawyers would like to say. Well, it's nice to be right and say you're right, but, prove it now. So can you prove it by failure? And this is why sheet piling is not causing failure in all these buildings when you see them go up, because it doesn't translate or correlate to this frequency right at X spot is exactly the frequency it's receiving over here 5 feet away at this concrete, steel, and bulkhead system, because that resonant frequency is going to be totally different. Totally different. Now, sometimes an oil truck goes up your street and no vibrating windows. Sometimes it goes up in the air, the vibration that is creating in the air pressure around it by this truck's engine and everything else. And it's the dynamics of it, how much oil's in the tank, etc. And how close it is to your house. And when it comes to that certain frequency, it gets right in line with your glass panes that happen to be loose also in the frames. And the window starts vibrating, the frequency of the window. It's matched it. And then you hear the window start shaking. And then all of a sudden they stop shaking. But if the truck could maintain it, ultimately it could cause the windows to crack. But the windows are able to flex a lot in that wooden frame. And if you confine the wooden frame, now the resonant frequency changes again. It's like a dampener. So it's not what you think it is. Now, if you want to learn more about resonant frequency, you look at the big towers. They have dampeners in them. These skyscrapers, they have dampeners in them. That's to change it when the wind's blowing around it, trying to make the tower move. They've got things that fluctuate and change with the dynamics of the wind blowing. They're not just, okay, we're going to stop this tower from swaying, we're putting a 10-pound weight. That's it. No, it has a fluctuating ability to it to change with the dynamics of the resonance being attacking the building. And if you want to follow Poisson's ratio, it would drive you crazy to do Poisson's ratio to all the dynamics of it, which I simply call equilibrium is taking place. It's finding equilibrium. And I don't mean the engineering term of equilibrium, but equilibrium as in all the time we're finding equilibrium. All right, the frequency range is 10 kilohertz to 40 kilohertz. That's huge, right? I'm sorry, I said kilohertz. To 40 hertz with 4.9 to 78.1 hertz resolution, the cycles. All right, so this is this sample that they did. It's not all concrete. All right, so it's not all that. It's not all the same. And here's something. Let's see if they do it. The easiest way to find the resonant frequency is to place the object next to a speaker and also place a microphone in it using sound. Attach an oscilloscope next to the object. Have the speaker play a tone at a given volume, and then without changing the volume, slowly change the pitch. And when it gets to, it's like when you get to a certain peak, you find out without having to cause it to break, fracture, you've already, through research, you can already determine, okay, it fractures the resonant frequency at this peak. And so we would need to maintain this peak and at a certain time frame, it's timeline. Remember, depending on the shape of it, it's going to might need a longer wavelength to get it to fracture. Cycle. Wavelength, no. So I get my wavelength and cycle mixed up. So wavelength, a longer, well, you need to get into the wavelength of that which you're trying to fail and maintain it. Maintain the vibration. And that's what all you're doing, the resonance, the vibration in it. Maintain it. You saw the eyeball thing I told you. And then it's not just instant that you hit 19 hertz, because I've crossed 19 hertz many times with you. I've communicated with you just now in my voice volume, but you didn't get a headache because I didn't maintain 19 hertz at your eyeball. All right, so it was 19 hertz at your ear maybe. I need your eyeball to get to 19 hertz, not your ear. See the difference? All right, and then maybe you got a big fat head. 19 hertz might not do it. I might need a little more than, well, no, because I said eye specifically. But you might need a higher volume on your skull than I would need on my skull to get to 19 hertz. You see the difference there? That's why it matters with the concrete wall. Where was the rebar placed? How is it in relationship to the deck? You'd have to do that. Now, with that said, let's look at what Ada stated about the wall and the guy falling off the bicycle, right? She didn't say the bicycle, the bicycle guy. So the frequency is over here. This is how ridiculous this is. They're driving the piles in here, and they're going in fast into the sand. We now know, as you know, sand has their hertz to allow it to slide in pretty fast. Your highest noise or your highest hertz is going to be closer to the sensor, which is at the surface. They didn't bury them down here. And we have another bulkhead over here, approximately 10 feet away. And then we got concrete approximately 12 inches thick in and out of the bulkhead system. And then we got a floor slab here. So you pick your poison, and I don't mean Poisson's ratio, of how you want to get over there. From here, and here's your machinery here, clamp. Let's just put a clamp on this thing. All right, so there's your tool there, your tooling. And then here is your sensor, and your sensor says, hey, look, we're moving at greater than half an inch. Oh, okay. Well, the sensor read that. You know, it depends again how the sensor was, but the over here, how much is it consolidating? How much is it moving? And then from there, it's got to find the resonant frequency of the steel to be able to add steel and concrete together, because now they're composite material, including the deck and the behavior of the dampener on top of it, which is the block wall. It is a semi-solid wall. How much of that is going to share? How much of it will amplify? How much of this will send it back because of the shape of it? Remember the ricochet effect. How much of it will it just send back and give you a false high reading? So the argument is that for the collapse now, the guy on a bicycle, treadmill guy. So let's do a treadmill here. Treadmill. Let's make a treadmill man here. And he's on a treadmill. All right, he's on a treadmill. Let's do the wheel here. And I'm just going to do that. All right, let's just delete. Treadmill man. Fuck, forget it. Here's the treadmill. Here's a tied to the treadmill. Let's delete. So he's running on a belt that's going that direction, and he's holding here. If he lets go of this for any reason, he's going off. He's probably, older people there. He's probably not going to be able to maintain that speed. Maybe he changed the speed. And our amygdala is so angry that the vibration was going on over there, and he was so pissed that day that he fell down. You ever hurt yourself and then turn to look to blame somebody else for you just hurt yourself? You know what? You just distracted me. I told you leave me alone or something. Well, it's because our amygdala does not want to admit that we own this one. So it's looking for an outside source for the accident. And it's so petty, the amygdala is, that even if you hit your finger with a hammer, what will you do? Instead of going, evaluate that you hit your finger with a hammer, let's take care of it. No. I don't do this anymore, but you grab the hammer and you might fling it. It's not your fault. The hammer just hit your finger, but because the amygdala wants revenge of anything that hurts the human, and it ultimately may not like might not like the idea of saying that was all my fault. So we got vibration over here. He falls down. He knows his vibration. Maybe he's looking through the window. He sees him doing it. He's distracted, and boom, his mind, and he falls down. He says, "Son of a bitch! It's these damn people here. You made me fall down and hit my chin. It was you." And they didn't like it anyway because he's got a file up here saying, "You're taking my parking spot." Even though they're in Miami, this building is located in Miami. This building is located in Surfside. So in fact, whoever's taking parking spots from this building is actually taking Miami parking spots, not Surfside parking spots. So I know it's a position a lot of you think that it's unfair. Well, stop thinking of fairness. When you think of the government, they own it all. It's an illusion that we own real estate. You can pay off your property all you want. You do not own it. You are still renting. You will have to pay school taxes. You will have to pay sewer and water taxes if it's related. You'll have to pay, what else? Just taxes in general, real estate taxes. Every year forever. Unless you find some way to get an exemption, which would be an amazing thing, and it wouldn't be permanent anyway. But then that would be the rare people. So unless you find an exemption, and the governments have those exemptions, they don't pay taxes. They're like, nope, we don't pay. We don't even care. And they make rules for thee, not for you. Not for you, not for thee. For example, they can have vacant properties. You have vacant properties. They can charge you fees for vacant properties. They tell you got to register your vacant properties. They don't have to register at the same time, nor do they have to pay fees for their vacant properties. They may stay vacant for years. Time doesn't run against the king either, so you can't take their property under any ownership by just using it. And they can take yours by just declaring that they need it for the better good of their tax roll. All right, so now they own this drive, that street, and they kept the intent by not breaking the law, if you will, by still allowing traffic to go to the beach, the right of way. But they still, and they maintain that however the agreement was written. So the right of way is still there, and it looks like apparently you could even drive a car, emergency vehicle, onto there and get to the beach if it's just so need to be. And we saw that literally with the firemen coming down there and also parking generators on that walkway, etc. That walkway, a generator wasn't just an easy generator to get to that location. So the compressor, whatever the hell it was. So the intent was Miami kept the intent of usage, as far as, and all they got rid of was, who did they displace? Did they displace Miami residents parking? Nope. Surfside residents parking. Well, they're not even in our town, right? If you think of it on their side. So who do we affect? We send out to our neighboring properties, but that's in another township. We don't have to send out to them. That's in another town. So we just deal with our town, our municipality, our problems. We fix this road here, not Surfside or whoever, because it was a private road, right? It's owned by the municipality, not the state. So they're allowed to do as they're allowed to do. So relax on that. Don't get upset about it. Now, as far as water running off there, you got water on this pool deck acting as a problem. It's already been there. Any deterioration and rust right here. Before that, unless unless you're going to claim that the rust we see on this steel over here all took place after this building was built, and including the vibration that caused the separation of the steel that then caused the rust. Well, that's not how it works, all right? That's not it. That steel has multiple reasons why it could have shown surface rust. Because we see the surface rust. We need to take the dimensions of it, look at what was the original profile of it, and then you can go from there and start evaluating that steel and looking at it forensically, determine each piece of steel, what's going on with it. We're doing imagery evaluation, but there is a level of forensics where you actually grab materials such as that steel, look at it, and under a microscope, and you can now start evaluating how that steel failed. You'd be you would be so easy, but you would take other data first, such as the testing, the sonar testing. You would cut that sample out, you would photograph it, you would measure it, you would survey it, so it's a perfect sample to take back and evaluate it. Frankly, nobody's at that level right now. Nobody's evaluating it that profoundly. Now we go to this now. So the resonant frequency of this with the slab on top in this is different than the resonant frequency of the glass over here, which you surely can get the glass rattling from over here just based on if the sound waves are changed going over this wall, mind you. Remember, there's a wall there, and they're over here. So it's going to hit this wall and do what? Ricochet back down to the sensor. That wall is all the way down. Where we have this failure, it's all the way over there to the planar box, the other planar box. The planar box is here. It's in line. It's over there, well, where the biker is, where you get the lower reduced planar box. But the planar box has its own resonant frequency it's got to go through. And it's got a new resonant frequency because it's got soil, plant bushes it's got to go through. And then it's got to vibrate the air around it again, past the bushes, make it over to this glass, any vehicles in the way, etc. in the way, make it through another planar box, I'm sorry, that's over there. Then make it over to this glass and start finding its resonant frequency to have it vibrate. Then it would have to find the resonant frequency of the concrete pad it's on, cause that resonant frequency of the pad over here that's elevated, remember 1'6" elevation over here at this point, cause the resonant frequency of that pad to elevate, and then it would have to cause the resonant frequency of the machine being on. We assume it's on because he said he was on it, right? He didn't say it was off or on, but we'll assume it's on. Then it would have to find the resonant frequency of an operating machine, match it, cause, and then it would be out of sync with him and throw him off. You see how the issue of resonant frequency, it's so many resonant frequencies that it would have to change from over here to here from the concrete pad, 1'6", then find the resonant frequency of a machine that already has its own resonant frequency going. And then this guy's frequency, whatever he's doing, then has to find his frequency and toss him off, cause him to fall. So you see that it's just too crazy to come up with that way over there. This is resonant frequency we're talking about. It will help 87 Park. I know my video helps 87 Park's lawyers to debunk their whole falling man. And this one they have to get some more data on. I mean, you know what? They can reach out to me and I can direct them to the other data to process this. The experts they would need in Florida to evaluate all this. And they do have access right now, I would think. No, that right-of-way still is probably owned by the municipality. Miami would have to give them permission, or court would have to give them permission to pull up the entire deck, the decking, all of it. Because if you leave the decking, you've got a damper now. You've got to duplicate the whole system, including the NV5's machine, the exact machine put there, because the calibration would have been based on so many days out. When was it calibrated? Then you'd have to put it there exactly. Soil temperatures, moisture temperatures, air temperatures, humidity temperatures of the air, and the moisture temperature of the moisture of the humidity of the soil. You'd have to pull up the existing piers, these things, so you can drive down. It's just not going to happen. Or you'd have to put the sensor in there, somehow start vibrating the soil where it would make this read a 5. If you can find the right location, where it would make it read the same reading with the sensor at the exact same position. And then without this wall in there, you're changing the dynamics of it. And without the pad, you're changing the dynamics. But just see if you can stay where this is at a half and see what it would take. If it's any frequency, take your readings off of this. And there's frequency vibrators, right? There's frequency vibrators, save. They're a resonant frequency vibration, looking at what they have here. Testing equipment. It's really cheap. I own a couple of versions of them. They're not that expensive, and well, I'm getting into my proprietary angle now. I am not going down there because this is, now we're messing with how I make my part of my living. So nope, I am not going down that end. I'm going to end the video because I almost started messing with my my wallet. Okay, so let's end the video with that and realize that to get over there, you had to have resonant frequency of that rolling machine. The glass is not the same as the building shaking. The concrete has its own resonant frequency, different from the wall system. Different from the wall system to the pad system, to how it interacted with the steel, how it interacted with the columns. Different from going through the floor. If you go through the floor with all the cars acting as dampeners, the tires and the weight on the pad. The shape of the echo of the garage itself. All that stuff is going to change. And if you don't think so, well, then just go out there and try to create I'm done. Look, I think this should end the resonant frequency videos on resonant frequency videos and sort of just shit-canning the idea that little bit of movement off of their range that they allowed for was somehow able to go through all that soil, materials rather, the aggregates, including sand, dirt, whatever, and start finding the resonant frequency of that steel with a small spike. Remember, I've crossed many times into where your eyeball would start fluctuating, and it's a different. I'm not going down there. You guys can research that. You can comment if you want on it, but think about people who might be evil. So try not to do that. That's why I don't do a lot of bridge videos. I see the failure mode in a lot of bridges, and I'm like, nope, can't do that video. Ultimately, that's what I look at when I see stuff. I see the failure mode, but I can't do videos of them because I don't know, somebody might be nasty and learn from my videos in that capacity, and then do something nefarious. And I keep my knowledge of that restrained. But I see the failure in so many bridges. I can look at a bridge and say, right there, that joint there fails, everything fails. I can look at things like that and see the failure of everything. All right, take care. Love you all. Thanks for watching. Bye.